so very good evening from India, and it is my great pleasure to attend the conference on Sustainable Industrial Processing Summit and Exhibition SIPS 2023. It is also I'm taking the chance to congratulate Professor Paul Santos Assis for a successful career, and basically for he is considered as a mentor or you can say as a motivator for the process metallurgist working in the iron and steel making and mining and metallurgy area like us for all over the world. And I wish him all the best for all his future endeavors. So with this, I'm going to start my presentation that is on the topic of modeling of large-scale industrial reactors involved in iron and steel making in an innovative manner. So as we know that the basis of analysis of any reactor is the heat and mass balance coupled with understanding of thermodynamics and kinetic constraints. So all plant design, capital cost, and technical evaluations are all dependent on all these calculations. If you look at any high temperature process in general, let it be in steel making or iron making or even in non-ferrous extraction also, so we deal with the dynamic interaction which is occurring at the very high temperature between the slag, metal, and gas phases altogether. And also there is going to become a lot of interaction with the dissolution of solids and a lot of other phenomena as well. We need to understand the reaction chemistry of the process, which involves thermodynamics, kinetics, and dissolution rates of solid charged material like scrap, fluxes, etc. So there is a coupled application of thermodynamics which is governed by sometimes the understanding of the computational fluid dynamics, like understanding the fluid flow, heat transfer, to evaluate the temperature, velocity, pressure variation in the reactor. And if I'm talking about the application at industry scale, so it requires the multi-scale automation control system where all these things are going to become the part of it. So a lot of mathematical modeling techniques are involved in the field, starting from fundamental models, which are based upon simple heat and mass balance, data-based models, and also evolutionary methods like artificial intelligence, machine learning, and so on and so forth. So basically, if I'm talking about the computational tools which could be used and which are being used in my group, so they involve the thermodynamic and kinetic-based models by using FACTS, and also the flow sheet based modeling, which involves the FACTS macro programming, ChemSheet, which uses FACTS data, and also the MetSim, and also the models which are based upon the first principles of artificial intelligence and machine learning. They are being developed by using the separate code in MATLAB and Python, and flow sheet models which we can develop by MetSim, ChemSheet, PyroSim. And also, we are using the Excel VBA solver. VBA is also having the programming capability. So if we develop the models, these are some of the snapshots basically which are just showing that how the models are looking on the screen when we develop about it. So if we talk about the process where we are dealing with the process which are involved in the iron making and steel making, starting from the steel making, secondary steel making, then alternate iron making. So in alternate iron making, the examples are like Corex process, MIDREX process, in secondary steel making, RS process, in primary steel making, EAF, BOF. So basically, we look at from the fundamental perspective, and I will give you some idea about that, how we can address them from modeling point of view. So if we talk about the modeling of any process, there is a dynamic interaction between the various phases. And if you talk about the interaction between the two phases, we need to involve the integrated reaction approach. So for example, if you consider slag metal reaction, which involves the multi-phase, multi-component mixed transport theory. So basically, I have applied it in one of my publications, and I've given the details also. So if we find it that because of the temperature, high temperature, although there is a thermodynamic equilibrium at the interface, but the transport of species to and away from the interface, they are governed by the mass transfer control kinetics, which are governed by the fluid flow, other things. So earlier people had worked on all these kind of concepts, but nowadays we can make a flow sheet based module, and we can define the fraction of all the phases which are coming from the bulk to the interface by using all those equations. We talk about the slag metal reactions. And let it talk about the gas solid reactions. So the gas solid reactions, for example, specifically in the case of say DRI making in the MIDREX process, or we can say that the blast furnace phenomena in the upper part of the reactor where the gas solid reactions are taking place. So we can develop a model where you can say that the kinetics is governed by the mass transfer control assisted by the diffusion coupled with the chemical reaction control and so on. So basically we can model it in terms of equations, but at the same time we can integrate it by the same coupled modeling approach which I just talked right now in a similar manner by having a lot of mathematical steps which I'm not going to define right now. You can go through my publications in the same way. So what we are going to do is that we are going to have a framework of coupling interfacial thermodynamic reactions with the kinetics, which may be governed by the mass transport in the liquid phase or the mass transport in the solid phase assisted by the diffusion, and we can develop a flow sheet based model using either the micro programming of the facts or maybe by the chem sheet using the facts data or by any other tool like SPEN plus what chemical engineers are using or Maximum, so on and so forth. So let us say that just I'm giving you an example of the basic oxygen steel making process where you can say that there is going to become multiple number of reactors starting from bulk metal reactor and then the free energy based minimization based reactor for metal gas reactor, that is a hot spot zone, or emulsion zone can be classified as a slag metal reactor, and the flow rate of the streams, they are governed by the mass transport criteria. In the similar manner, we can define the multiple reactors for the gas solid reactions for the MADRAS process as well, where the kinetics is being defined as you can say that the fraction of the gases which are able to react with the solid in the equilibrium reactor or not able to react or they are being bypassed. So basically, based upon the concept which I have talked so far, in my research group at IIT Madras, we are working on development of mathematical models, and we have worked on the oxygen steel making process. We have worked on the modeling of RS degassing process, Corex iron making process, and a MADRAS process reactor as well. So I will just, without taking much time, I will quickly just give the overview of what activities which I have taken on all the modeling of all these parts. So first I'm going to talk about the comprehensive model of the Corex process reactor. So basically one of my student, Mr. Sri Shrilan, has worked on it a few years back, and now he's a faculty in another IIT. So what the approach is that if you look at the Corex process, so basically, it's a combination of two reactors. One is the melter gasifier, and on top of it, there's a reduction shaft. In the reduction shaft, lump iron ore, pellets, and sinter, along with the flux, they combine. They are being charged. And after pre-reduction, so the pre-reduction occurs by the reducing gases coming from the melter gasifier, and then the pre-reduced material is going into the melter gasifier, and then the primary oxygen and secondary oxygen is being supplied. The coal or coke is directly charged into the melter gasifier. So from fundamental point of view, there is a competition between the pre-reduction of the iron ore in the reduction shaft and then followed by the melting of it in the melter gasifier and also the post combustion. So basically how these phenomena are controlled are going to give you the dynamics of this reactor, and based upon that we can efficiently utilize the raw material, and the process can be run very effectively and very efficiently within the margin of permissible limits of CO2 emissions and energy consumption and raw material consumption, and particularly the coal or coke, which is, you can say, our concern. So basically our motivation was to develop a comprehensive model where the thermochemical part of study of the heat and mass balance was performed. So a static model was developed. And then the thermodynamic part was simulated the chemical reactions in the equilibrium zone of the melter gasifier and reduction shaft. So the kinetic part was to simulate kinetic limitations in the reduction shaft. So basically what we did is that there have been a number of activities which occurred in this work, that a single zone static thermochemical model was developed, multi-zone thermodynamic model was developed, and then a separate kinetic model reaction shaft was developed because we are not able to predict the phenomena based upon thermodynamics. So kinetics was required to be considered, and graphical user interface. So I will not talk about the last one. So based upon the, so now I'm talking about the static model. So in the static model, there were a lot of elemental balances and that oxide balances in the slag, they were performed. Basicity was calculated. Then the heat balance was performed to estimate the heat demand and heat evolved and heat losses. then degree of post combustion was calculated, degree of metallization was calculated, and we performed all these calculations by making a comprehensive mathematical model which was programmed in by using MATLAB, and basically we have validated it with the industrial data, and basically not only validated, but we have seen that what is the effect of various operating parameters in terms of metallization or post combustion ratio on various achievable targets. So what we find is that basically the metallization, if you basically with the increase in the metallization, the requirement of the coal decreases, which is very much obvious, and we were able to predict the flux requirement also, oxygen requirement also. And our results were in very good agreement with the industry data. The similar exercise was being done with respect to the estimation of slag volumes as a function of metallization, and there also agreement was made. So the conclusion was that with the increase in the post-combustion ratio, it decreases the coal requirement, flux requirement, and oxygen requirement. Similarly, with the increase in the degree of metallization, it decreases the coal requirement, flux requirement, oxygen requirement, and export gas produced. So all these phenomena are well known, but we are having a modeling framework for that. So if you talk about a multi-zone thermodynamic model, so where the process is divided into the number of zones, and basically all these kind of things which I had already talked about, the concept were applied. I'm just quickly skipping it. And basically we have plotted the temperatures of various reactor zones as a function of metallization, and the composition of waste gas and various reactors. So all these things are already published in the literature, and one can have a look at it. And also the effect of coal grades on the hot metal compositions. So basically with the increase in the metallization, silicon percentage is decreasing. With the increase in metallization, sulfur it is having some kind of different behavior. The phosphorus percentage also decreases with the increase in the metallization. Okay, and similarly for the manganese, actually the reverse phenomena was observed. So the conclusion was that with the single zone static model, the increase in the metallization and the effect was studied on the amount of coal, flux, and oxygen requirement. And the multi-zone thermodynamic model, the results were in good agreement for high metallization, and effect of degree of metallization over post-combustion ratio was also observed. Now I'm going to talk about the second problem that we did with my another student, Mr. Prashanjit Singha, that he has developed a flow sheet based model for oxygen steel making process. So here, that oxygen steel making process is one of the well-known process which is responsible for the almost 60% production of the steel. So here the hot metal, which is saturated with the carbon, is directly charged into a vessel where it is oxidized with the help of oxygen lance, where the oxygen is being supplied at very high velocity and very high pressure inside the metal bath. So a lot of chemical reactions which are responsible for a very fast rate of decarbonization, and as well as the removal of other impurities like phosphorus and sulfur and all those things do occur. Without going into the detail of this process, I'm coming to the point that how we model it by using this concept of the flow sheet model. So the total BOF process were divided into number of adiabatic stoichiometric reactors, 2 bulk chambers, and 2 free energy minimizers. And in all these cases, basically we have used fact-based software, and computations were done in a repetitive manner. So basically FT oxide, FT MISC, FTPS, all these databases were selected for calculations, and the equilibrium module and macro program was developed. So basically in this present study, the kinetics was considered to be governed by mass transfer limitations, and that are related to the mixing of the reactor. So this depends on the rate of energy input to the system by the means of top brewing, LAN, and as well as you can say that evolving CO inside the reactor and bottom stirring phenomena, all those things. So all these things are defined in terms of equations. And then what I'm going to do is that we have defined certain parameters, kinetic parameters given as alpha, beta, and delta that are calculated by the mass kinetic considerations, and they are giving the fraction of metal which are going into the various reactors from the bulk reactor. Similarly, other associated phenomena like dissolution of scrap, dissolution of flux, etc., they also go on side by side actually. So they are also the part of the model. What we have predicted is that we have predicted the decarbonization rate as a function of blowing time for the various values of alpha parameter. That is, we can say that the kinetic parameter for the fraction of metal that is going from the bulk of the metal to the hot spot zone. And then basically the temperatures of steel, slag, and hot spot and emulsions, they have been estimated. And then based upon the hot spot temperature, which is very much close to between 2000 and 3000 degrees centigrade, we have concluded that this may be the real representation of the process which is going on. So similarly for the slag volumes also we have predicted, but for example, for some cases the slag trajectory is very much similar to what we observe in industry. And similarly, that carbon trajectory and silicon trajectory and all these things are also predicted. So the conclusion that I'm giving, that what we got from this model, that a dynamic model was developed to simulate the oxygen steel making process based upon the multi-reactor based approach, and multi-component mixed transport control method was used to study the decarbonization rates and their contributions coming from jet impact zones, slag metal emulsion, and bath boiling for different levels of mixing. So basically, what we found that higher mass transfer coefficient in the metal bath resulting in higher contribution by the hot spot decarbonization, lowering the levels of FeO formation, and in fact, lesser emulsion contribution decarbonization, and vice versa. So basically, the benchmark of the hot spot temperature was in the range of 2000 to 3000 degrees centigrade. Then, as per the model results, the major contribution of decarbonization comes from hot spot reactions in most of the process. However, by the end of the process, it was governed by emulsion actually. So basically, this model is still under development, and which can be used as a guiding tool for BOF process by incorporating more and more details. And but our objective was to understand the decarbonization phenomena and its contribution coming from the hot spot zone versus emulsion and versus other, bath boiling, and that we were able to predict it in a very efficient manner. Now, the last, in fact, I will take only 3 or 4 minutes. The last modeling which I'm going to talk about, the flow sheet based modeling for the mid-range process reactor. So there, another student, Mr. Sunil Yadav, had worked, and he has published a paper in metallurgical transactions. So that is now available online. So with a similar logic, we have used the flow sheet based modeling approach for the modeling of mid-range reactor as well. So as we know that it is a shaft furnace based approach to produce DRI by using the iron ore in the form of the pellets and lump. So the iron ore is being charged into this shaft furnace from the top, and then it descends to the gravity and reacts with the carbon monoxide and hydrogen, which is ascending. So it's a counter current reactor. So the product is basically in the form of steam and CO2, which is coming from the off gas, and that high temperature waste gas, which is laden with CO2 and steam, that is being used for the refining of the natural gas. In fact, this process can also take some intake for the hydrogen also. That is a matter of investigation, that if we can increase the hydrogen intake into this process, and basically and also the other kind of gases which do not contain carbon, like syngas or coke oven gas, if they can be integrated or channelized with the reducing gases entering into the process, so that would be that is a part of investigation for this model. So again, for this work also, a multi-zone thermochemical model was developed utilizing thermodynamics and coupled kinetics and heat and material balance to predict the operational parameters and estimate the impact of different rates of materials on production rate, metallization, carbon content, top gas compositions for the mid-range iron making process. It was validated with industrial data to be used as a guiding tool for the actual industrial operation of the mid-range process, and we found a good agreement with the industrial data results. And this model has been used to study the effects of variation in process parameters with an objective of efficient utilization of raw material and reducing gases. And basically, the objective was to maximize the production and metallization. So finally, the effect of replacing some coke oven gas and natural gas in the cooling section was also studied with the help of the same model framework. So this is the work plan. Actually, I'm just skipping this slide. This is the flow sheet actually. So basically, the process has been developed and a lot of calculations have been made in a repetitive manner till it has been matched with the industry data. So I'm skipping this one also. And basically what we did is that we have divided the process into the number of reactors which are connected to the flow of streams. And here also the kinetics of the gas solid reaction is being considered with a fraction of the gases which are going into the reactor and which are being bypassed actually. So basically in this way we were able to predict the production rate, metallization, exit gas flow rate, compositions, all those things basically. So we are having a framework based upon this, not only MADRAS but any shaft furnace process for iron making can be investigated, and we can see the effect of various kind of utilization of the new type of the raw material or new types of the fuels, and the fuels which does not contain carbon, and we can test it with the injection of the hydrogen and syngas, and with other things also as well. So my results of the model are in very good agreement with the industry data as far as the metallization is concerned, carbon content is concerned, exit gas flow rate and productivity is concerned. In fact, exit gas compositions are also in very good agreement with our model results. Similarly, the effect of reformer gas, so all these things are also calculated. And similarly, the effect of natural gas and coke-oven gas replacement is also being considered. But we need to validate it with the industry result, that we have not done it so far. So the final conclusion is that a thermodynamic model for the mid-rex iron making reactor was developed using FactShares software and micro facility. And basically, it was again developed by the similar approach, that conceptualizing the mid-rex process reactor into the number of equilibrium reactors connected to the flow of streams. And the validated model can be used for studying the effect of varying various parameters. And basically, it is in agreement with industry data, and the model can be further developed to study the effect of various other things which this I have talked about. So I think with this, I think I'm concluding my presentation, and I again thank the organizers of SIPS for giving me the opportunity to present my paper, and I'm very much honored to express my viewpoints. Thank you very much.
Thank you very much, Professor Shukla. We have time for maybe 2 questions, please. The audience. Anyone? No question? No question? So I have one question, Professor Shukla.
Yes, sir.
Yeah, you are presenting a kind of a model that is very average in the reactors. But you see, the metallurgical processes are very complex, and mostly they do not reach the equilibrium condition that you assume in many of your batching reactors. So how are you thinking to solve this kind of things, or to approach this problem of no equilibrium and a multi-scale reactor in a special dimension, for example?
Sir, I agree. Thanks for this asking the question. Sir, I agree with your point that metallurgical reactors are not in equilibrium, and they are far away from the equilibrium. So that is why this approach has been adopted, where I am not saying that the entire reactor is in equilibrium, but I can see that say that the localized regions may be in equilibrium. For example, the interfaces, the two phases are meeting with each other, they may be in equilibrium because the kinetics is very fast at high temperature. Secondly, for example, if you are talking about the liquid medium where the slag metal reactions are taking place, I can say that the process may be very much close to the equilibrium, where there is very efficient mixing. So for example, for the case of oxygen steel making, if we talk, we can say that the thermodynamic equilibrium may be very much in the hot spot zone, or the regions which are receiving more mixing energy, or particularly I can say that the middle part of the process where there is an extreme level of turbulence into the reactor, that we can say that the behavior of the reactor may be very much close to a fully mixed reactor. I can say that the entire reactor may be very much closer to the equilibrium for the time when there's a lot of turbulence and mixing into the reactor. But if the reactor is not in equilibrium in totality, what we can do is that the bulk reactor, which is not in equilibrium, whereas there's some localized region which are in equilibrium, we can connect them through the flow of streams actually. And those flow of the streams may be defined by kinetic parameters, maybe by the velocity calculated by some CFD software, or maybe some mass transfer coefficient, or maybe some diffusion coefficient. So here my idea is that I'm not saying that the process in totality in equilibrium. I'm saying that some localized regions are in equilibrium, and those regions are defined with the multiple number of reactors into the system, and then they are interconnected with the bulk regions which are not in equilibrium, and the process is divided into a number of time steps, and then in this way the phenomena is being governed, and we make certain calculations, and then by validating the process in a cyclic manner with the real process, we again recalculate those coefficients, and in this way finally we are able to arrive at the coefficients which are the true representation of the actual process. This is my strategy.
Okay, okay, thank you. I had another somewhat long question. Maybe you can answer very shortly. As you see, we have some experience with working with thermocouple, and thermocouple developed a special framework to do this kind of modeling by batching and reactors interface model. Do the fact stage also has this kind of interface, or you must do your programming by yourself?
Sir, actually, FactSage, people are working, I will say, much extensive work on the process side, actually, as well as the database, actually. They are more, I mean to say, they are available in the FactSage since a much longer time before that thermocal has started. But since I have the long years of experience of working with the FactSage, so I can tell more about it, and I'm finding it very much comfortable and useful to model any kind of process phenomena. But the only thing is that, for example, whether it's a ferrous or non-ferrous, you need to have the access to the database, actually. For example, if I want to work in the area of copper or nickel or other systems, I need to purchase those database. But for practical conditions, you know that FactSage databases and FactSage modeling is working effectively, at least for me. For thermocal, actually, I do not have much experience, so maybe I cannot say, or maybe those who are using, they can be in a better position to answer them. But yes, based upon our experience, because all these kind of models are directly applied into the industry, and sometimes they are being tested with the industry results also. So if we find any kind of mismatch between our results and industry results, we can update it to the FactSage that okay, they can again retune or recalibrate their data also. And this is how I think most of the database which FactSage has, especially on the process side, they have been recalibrated based upon the work by various researchers in the laboratory and as well as the industry as well. So the whole thing, the whole phenomena depends on the accuracy of the database. If they are well tested, well calibrated with the real work, it's good enough. But if they are not, then perhaps we need to work with the FactSage or any other software provider to recalibrate those data with the help of industries or with the help of academic institute or laboratories.
Okay, thank you very much. I think it's a simple event. Okay, wait a moment, Professor Tadeu Sui, like to make one question. Microphone.
Thank you very much. Thank you, sir. Thank you.
Thank you very much for your nice presentation. My name is Tadeu Usui, Osaka University, Professor Emeritus. Not working. Okay. I'm always thinking, comparing the blast furnace based oxygen process. It's very nice, but it needs carbon. However, in a forex process, you also use carbon, but MADRAS process, in that case, the solid iron oxide having gangue mineral, and you talk about the basicity, but the solid state reduced iron oxide containing a gangue mineral, so the basicity control in the steelmaking stage. We need limestone much more, and slag is not good to use, very harmful in comparison to the blast furnace slag. That's a byproduct for blast furnace cement. So that's the point. Even the Brazilian iron ore, very high grade. In Japan, the low grade iron ore we often use, but in both cases, there is a gangue mineral. So how we can overcome the slag in the steelmaking stage? We can't use harmful slag comes. Do you have any idea to overcome this problem?
Okay, so thank you, sir, for this question. It's a very good question. And in fact, you know that the gangue mineral inside the iron ore are the main reason for this slag generation. And basically, for example, we know that in the case of blast furnace, we are having a limit of the gangue material, so that is why it cannot take the iron ore beyond a certain Fe level. But in the case of Corex process, actually, you know, already we are having a lot of slag volume which is coming from the ash content of the coal. Actually, so we already have a lot of volume of the slag. And depending upon that, we need to charge more and more amount of limestone. So it is going to have another cyclic effect. And if we have the gangue mineral in iron ore also as well, it is also going to multiply the problem to increase the slag volumes further. And it will also require more amount of coal because it is having the oxide material which is required to be melted. So basically, definitely, you're right that there also the slag volumes are going to be more if you use iron ore with high mineral content. But with the help of where my model can help, with the help of this modeling framework, you can simulate various conditions without much need of experimentation, and maybe one can validate some of those conditions in a pilot scale or maybe at an industrial scale and find out the limitation. That means what could be the maximum permissible gangue mineral containing iron ore, or you can say that the minimum Fe content of the iron ore which you can charge into the Corex process without having any adverse effect over the process phenomena. So with the help of the model, they are going to use as a guiding tool to help in that way. Again, depending upon the iron ore presence in the different part of the world, and similarly the coal present. For example, if you want to do this study for the case of Brazil, or for the case of say South Africa, or for the case of any other location, yes, we can test our model for those parameters, and some of them can be tested in industry also if the industry is operating in that region. So there it is possible. Yes, it is possible to define the limit actually mathematically, that up to what level you can go actually.